So you've probably heard all the buzz about AI agents, right?
Yeah.
They seem to be everywhere, really taking the tech world by storm.
Oh, absolutely. The adoption rate is pretty staggering.
Yeah, I saw figures like over half of large IT enterprises are already using them. And something like 21% adopted them just last year alone.
It's a huge economic wave, no doubt. We're talking, what, over $5 billion valuation late last year?
And projected to hit nearly $200 billion by 2034. It's massive.
And for a long time, the engine driving these agents, the core intelligence, has really been large language models, LLMs.
Like the big generalists, handling everything from, high-level strategy down to the nitty-gritty tasks.
Exactly. And a ton of capital has flowed into supporting them. Think about cloud infrastructure, something like $57 billion in 2024 alone, and a big chunk of that is for these LLMs.
Okay, but here's where it gets really interesting for our deep dive today.
Yeah.
What if that whole model, this reliance on these massive general-purpose LLMs, what if it isn't actually the best way forward?
You mean not the most efficient or suitable?
Or even the most economical path, especially for these agentic AI systems. So today, we're diving into some fascinating new research. It's from NVIDIA and the Georgia Institute of Technology, and they make a pretty bold claim.
Which is?
That small language models, SLMs, are actually the future of agentic AI.
Okay, that is bold. A real paradigm shift potential.
Exactly. So we're going to unpack why this paper argues for that shift, what the benefits could be for you listening out there, and importantly, what the hurdles might be.
Sounds good. So what does this all mean for where AI is heading?
Let's dive in and find out. Okay, First things first. We're talking about small language models, SLMs, but small in the AI world.
Yeah.
Well, it can mean different things.
Yeah.
How are they defining an SLM in this research?
Right. What's the dividing line between an SLM and an LLM here?
Yeah.
What's interesting, and I think quite smart, is that their definition is really practical. It's focused on the user's experience. Oh. So an SLM is defined as a language model that's compact enough that it can actually fit onto a common consumer electronic device. Think your laptop, maybe even a high-end phone down the line.
Right.
And crucially, it has to perform inference, that's the computation part, with latency low enough to be genuinely practical for a single user's agentic requests. Real-time interaction, basically.
Got it. So practical speed on everyday hardware. Is there a parameter count attached to that, roughly?
For now, yeah. For 2025, they're generally talking about models below, say, 10 billion parameters. And an LLM, well, that's just anything bigger than that, anything that doesn't fit the SLM description.
Okay, so the core argument then is that these relatively smaller models, these SLMs, are already powerful enough, they're operationally a better fit, and necessarily more economical for agentic AI.
That's the thesis. It's a strong position, especially given, like you said, how much focus there's been on just making models bigger and bigger.
Yeah, it definitely challenges that sort of bigger is always better assumption many of us have fallen into with AI. So what does the research actually say about the capabilities of these SLMs right now? Are they genuinely up to snuff?
Well, yeah, this is where it gets really compelling. If you look at the bigger picture, the relationship between model size and capability, the scaling curve, it's actually getting much steeper.
Steeper, meaning?
Meaning you get more capability improvement for smaller increases in size than before. So these newer SLMs are surprisingly close, capability-wise, to older generations of much, much larger models. It's not just a simple linear improvement anymore.
Okay, can you give us some concrete examples, like specific models?
Absolutely. Let's take Microsoft's Phi 2. It's got just 2.7 billion parameters, tiny by today's LLM standards.
Right.
But it achieves common sense reasoning and code generation that's pretty much on par with models that were like 30 billion parameters, and it runs about 15 times faster.
Wow, okay, 15 times faster.
Yeah. Or look at their Phi 3 small 7 billion parameters. It matches capabilities seen in 70 billion parameter models from not long ago.
70 billion, that's a huge difference.
It is. And NVIDIA has their Nemotron H family. They have models from 2 up to 9 billion parameters. Again, offering instruction following and code generation comparable to 30 billion parameter LLMs, but using way fewer computation operations for inference. Any others?
Oh, yeah.
Hugging Face has the small LM2 series. These range from a mere 125 million parameters up to 1.7 billion.
Million.
Wow, tiny. But they can perform on par with 14 billion parameter models from the same time, and even match 70 billion models from just 2 years prior on things like understanding, tool calling, following instructions. It's really quite remarkable.
That is incredible. So we're seeing models a fraction of the size doing just as well, sometimes maybe even better in specific ways, and much, much faster.
Exactly. It seems like capability, raw problem-solving ability is becoming the key constraint, not just the sheer number of parameters.
And you mentioned tool calling there. It sounds like even these small models can be boosted using techniques like tool augmentation to compete with bigger ones. Can you maybe quickly explain what that means for listeners?
Yeah, great question. Tool augmentation is basically teaching the model not to try and know everything itself. Instead, it learns to recognize when it needs outside help.
Like using a calculator.
Exactly, like using a calculator for tricky math, or maybe accessing a database for a specific fact it wasn't trained on, or calling an API to, say, book a flight or check the weather.
Okay. So it's about using external resources smartly.
Precisely. It's empowering the model to leverage the outside world rather than trying to cram all possible knowledge into its own parameters.
Right.
And that's a real game changer for making smaller models highly effective for agents.
Okay, so if they're powerful enough and they can use tools, what about the money side, the cost? Is this where SLMs really pull ahead? Because cost is, let's face it, a massive factor for anyone deploying AI.
Absolutely. This really brings up a critical point about resource allocation efficiency.
Right.
Serving a typical, say, 7 billion parameter SLM is somewhere between 10 and 30 times cheaper than serving a big 70 to 175 billion parameter LLM.
10 to 30 times cheaper.
Yeah. In terms of latency, how fast it responds, energy consumption, and just the raw computational operations needed.
Wow. That's huge.
It is, and that dramatic cost reduction is what enables real-time responses at scale, which is absolutely crucial for AI agents to feel useful and interactive. The operational costs for inference, for just running the model, are just so much lower.
Why is that, fundamentally? Less computing power needed.
Essentially, yes. They require significantly less parallelization. You don't need to spread the work across as many expensive GPUs or different compute nodes. It's just less demanding, hardware-wise.
Okay. And what about the development side? Fine-tuning them, adapting them. Is that quicker too?
Oh, definitely. That's another big win. SLMs can often be fine-tuned in just a few GPU hours.
Hours, weeks.
Exactly. Not weeks or months like with giant LLMs. This means you can add new behaviors, fix issues, or specialize the model for a new task practically overnight. That kind of agility is, well, it's a game changer for development cycles.
And you mentioned running them on consumer devices earlier.
Right. That leads to true edge deployment. They can actually run locally on consumer-grade GPUs. Think about NVIDIA's ChatRTX platform, for example.
Yeah.
This allows for real-time, offline agentic inference. So lower latency because the data doesn't have to go to the cloud and back, and also much stronger data control and privacy because the processing happens right there on your machine.
That's a huge plus for privacy-sensitive applications. So it's not just about running them cheaper, but also building, adapting, and deploying them much faster, more flexibly, even directly onto user devices.
That's the picture, yeah. It's a fundamentally different operational model compared to centralized massive LLMs.
And does this enable different kinds of system design?
It really does. It leads naturally to this more modular, almost Lego-like design philosophy.
Lego-like?
Yeah, instead of relying on one single giant monolithic model trying to do everything, you can build agent systems by composing several small, specialized SLMs.
Like different bricks for different functions.
Exactly. This component-based approach makes the whole system potentially cheaper to build and run, faster to debug if something goes wrong with one piece, easier to deploy updates for specific functions, and just generally better aligned with the very diverse, often quite narrow needs of real-world agent tasks.
Okay, so beyond just being powerful enough and cheaper, what else makes these smaller models inherently a better fit for agentic systems? What's the kind of operational advantage?
Yeah, this brings us squarely to, let's call it, operational suitability.
Right.
Think about what AI agents actually do most of the time. Often, they're only using a tiny fraction of an LLM's vast general capabilities for any given task.
Makes sense. You don't need Shakespearean prose to schedule a meeting.
Precisely. So why use this giant cognitive sledgehammer when a finely tuned scalpel, which is what a specialized SLM can be, will do that specific job perfectly, faster and cheaper?
That's a great analogy that really resonates. Using a surgical laser versus a jackhammer. I can see how some LLM-based agents might feel like the latter right now.
Exactly. A fine-tuned SLM can be trained to perfectly handle those narrow, repetitive, often non-conversational subtasks that actually dominate a lot of agent workflows. Think data entry, simple classification, pulling specific info.
And what about interacting with other systems? tools and APIs.
That's another key area. Agentic interactions often demand very strict formatting. Outputs might need to be in perfect JSON or XML or some other structured format for tool calls or passing data along.
Right, machines talking to machines need precision.
They do. And SLMs can be precisely trained, fine-tuned for these single specific formats. This drastically reduces the chances of, hallucinatory mistakes or formatting errors that a more generalist LLM might make when forced into a rigid structure it wasn't primarily designed for.
Okay, that makes sense. Better adherence to rules.
And another point is that agentic systems are often, naturally heterogeneous. It's like building a team.
A team of models.
Kind of. An agent system can effectively use multiple models of different sizes working together. You might have a larger LLM acting as the sort of root agency or the orchestrator for complex high-level reasoning or understanding nuanced human requests.
Okay, the big picture thinker.
Right. But then it delegates. It could call upon various specialized SLMs to handle specific subordinate tasks or execute particular tool calls really reliably.
So you get the best of both worlds. Broad understanding when needed, but hyper-efficiency for the routine stuff.
That's the idea. The research paper actually has a figure illustrating this. In one example, a language model agency, you have one main LM interfacing with the human and orchestrating, but it calls out to tools or even other, perhaps smaller LMs for specific jobs. Or in another setup, a code agency, there's a dedicated controller model orchestrating all the interactions, potentially mixing and matching LLMs and LLMs based purely on the complexity of each subtask. It's about optimizing the whole workflow for both power and efficiency.
That flexibility seems really powerful.
It is, and it fundamentally supports democratization too. If SLMs are cheaper and more flexible, it means more people, more organizations, smaller teams can actually afford to develop and deploy sophisticated agents.
Which could lead to more innovation.
Exactly. More diverse perspectives, tackling problems, potentially reduced biases because you don't just have a few giant players dominating, and just an overall acceleration of innovation in the whole field.
That's a really important point. And there's one more benefit you touched on earlier.
Yes, the data aspect, the very interactions within these agent systems, the inputs, the outputs, the tool calls, the successes, the failures, generate incredibly valuable, targeted data.
Data to improve the system itself.
Precisely. This data can be continuously fed back to fine-tune and improve those specialized expert SLMs, making the entire agent system smarter, more reliable, and more efficient over time. It's a built-in improvement loop.
Okay, this all sounds incredibly compelling. Powerful, cheaper, more flexible, better suited. But, I can already hear the arguments brewing from the established LLM camp. What are the common objections people raise against this kind of shift? How does the research tackle those? Because, let's be honest, changing course in a multi-billion-dollar industry is never straightforward.
No, it definitely isn't. And that raises the obvious question. If SLMs are so great for this, why aren't they already the dominant approach in agentic AI?
Right. What's the pushback?
Well, one very common argument is basically that LLMs are always smarter. This is often linked to something called the Semantic Hub Theory.
Semantic Hub Theory. Okay, what's that?
The idea is that LLMs, because of their sheer size and diverse training data, develop a superior, more general understanding of language and the world, this kind of central semantic hub. And this hub, the argument goes, lets them integrate diverse information more effectively, making them inherently better, even for relatively narrow tasks that might seem simple.
So even for a specific task, the broader context helps.
That's the claim. And proponents often point to scaling laws, the observation that bigger models tend to perform better on benchmarks as sort of proof for this inherent superiority.
But the paper we're discussing pushes back on that, doesn't it? It's not quite that simple.
Exactly. The rebuttal in the paper makes a couple of key points. First, many of those scaling law studies assume a constant model architecture while just increasing size. But that's not really true for modern SLMs.
So the smaller models might have newer, more efficient designs.
Precisely. They often incorporate architectural innovations. And second, the flexibility of SLMs means they can be very easily and cheaply fine-tuned to achieve extremely high reliability for the specific tasks required by an agent. You don't necessarily need the whole semantic hub if you just need perfect JSON generation for one API call.
You just need to be really good at that one thing.
Right. And crucially, the paper argues that advanced agentic systems are designed to break down complex problems into simpler subtasks. When you decompose the problem effectively, The need for that super broad, general semantic hub understanding from the LLM is actually minimized in many, if not most, of the individual model calls.
Okay, so task decomposition changes the game. What about the economics, though? I could see someone arguing, sure, running one SLM is cheaper, but managing a whole zoo of specialized SLMs must be complex, right? Balancing the load, the infrastructure, maybe it's not cheaper overall. Does the research address that?
That's a very fair point, and it's another common objection. Let's call it the economy of scale for LLMs argument.
Right.
The argument is basically that it's harder to fully utilize computing resources and balance the load efficiently when you have many different specialized SLM endpoints compared to just running one big generalist LLM that handles everything. Plus, the costs of setting up all that infrastructure and maybe retaining talent with diverse skills, it adds up.
So, potential hidden complexity costs.
Potentially, yes. However, the research counters this by highlighting recent significant improvements in things like inference scheduling and system modularization. They mention tools like NVIDIA Dynamo, for instance.
What does that do?
It's basically a system that helps intelligently manage and optimize how computing resources are allocated across different AI tasks and models. These kinds of advancements offer really unprecedented flexibility in managing diverse workloads on computing clusters, making it much easier to efficiently run multiple SLMs.
So the management tools are catching up.
They are. And furthermore, the general trend is that the setup costs for infrastructure are consistently falling. Hardware gets cheaper, software gets better. So while it's a valid concern, the jury is maybe still out on the long-term cost balance, but the trend seems to be moving in favor of making distributed, specialized SLM setups more economical.
Okay. And then there's just inertia, right? The industry has invested so heavily in LLMs already.
Absolutely. Industry inertia is always a factor. LLMs have a significant head start in terms of deployment, optimization tools, existing workflows, developer familiarity. A lot of the current industry effort and talent is focused there.
It's hard to turn the ship.
It is. The paper fully acknowledges this inertia, but it argues that the combined weight of the advantages, the surprising power, the dramatic economic savings, the operational flexibility and suitability for agent tasks, that this collective case for SLMs is strong enough that it could plausibly overturn that status quo eventually.
So if the technical and economic arguments for SLMs are getting stronger, why are we still seeing so many big generalist LLMs at the heart of most AI agents today? What are the practical sort of day-to-day hurdles holding back a faster shift?
Yeah, it's a good question. Touching on the practical realities, one major barrier is simply the sunk cost, the huge upfront investment already made.
Billions poured into LLM infrastructure.
Exactly. Massive capital bets have gone into centralized LLM training and serving infrastructure. Consequently, the industry built tools, workflows, and even optimized hardware around that model, often overlooking or deprioritizing the development needed for efficient, decentralized SLM deployment.
So it's partly just that the existing roads are paid for LLMs, not SLMs yet.
That's a big part of it. Another related issue is the focus of benchmarks, how we measure good AI.
Right.
SLM development often gets measured against the same broad, generalist benchmarks as LLMs, like answering trivia or writing essays, but these don't always capture specialized agentic utility very well.
So they might look worse on a general test, even if they're better for the specific agent job.
Potentially, yes. The paper points out that when you evaluate them specifically on agentic utility tasks, like reliable tool use or structured data generation, SLMs often outperform much larger models. But that nuance gets lost if everyone's just looking at the big general leaderboard scores.
Interesting. So the way we measure success needs to adapt too.
It probably does. And finally, there's simply a lack of awareness, maybe. SLMs just don't get the same level of, marketing hype and press attention as the latest giant LLM release.
Yeah, GPT-5 gets headlines, maybe 5.3 Mini doesn't quite as much.
Right. Even though these smaller models might be perfectly suited, or even better suited, for a huge range of industrial and consumer agent applications, they're just not as visible.
Okay, so it sounds like these barriers aren't really fundamental flaws in SLM technology itself, but more practical, market-driven, and maybe perception-based challenges. And it sounds like new technologies and growing awareness are starting to address them.
I think that's a fair summary, yes. The underlying tech seems increasingly solid. It's the ecosystem and adoption that needs to catch up.
All right, this is where, as they say, the rubber meets the road. For businesses or developers out there who are currently using LLMs in their agents and are intrigued by this SLM approach, what does the research suggest is the practical way forward? Is there a roadmap for converting LLM-based agents to use SLMs?
Yes, absolutely. The paper doesn't just make the argument. It actually outlines a pretty clear 6-step algorithm for doing this conversion, leveraging the specific nature of how agents work.
Okay, step 1.
Step 1 is secure usage data collection. You need to start systematically logging all the agent calls that aren't direct human-computer interaction. So think internal calls between agent components, calls to tools, etc.
What kind of data?
Inputs, outputs, the specific tool calls made, parameters used, maybe even performance metrics like how long each call took, the latency. The paper sort of visualizes it as putting an optional logger on these internal agent interactions.
Okay, capture what the agent is actually doing internally. Then what?
Step 2, data curation and filtering. Once you've gathered enough data, and they suggest tens to hundreds of thousands of examples as a decent starting point, you need to clean it up.
Clean it how?
Critically, remove any sensitive information. You absolutely need to strip out PII, personally identifiable information, or PHI-protected health information, things like names, addresses, medical details. Got to be careful with privacy and compliance.
Makes sense. Okay, data collected and cleaned. Step 3.
Step 3 is task clustering. You apply techniques, could be automated, could be manual analysis, to look for recurring patterns in that cleaned data. What kinds of requests keep popping up? What specific actions is the agent taking repeatedly?
The goal be?
The goal is to identify specific, narrow, well-defined tasks that a specialized SLM could potentially take over. Things like recognize user intent from this type of phrase, or extract these 3 specific pieces of data from this document format, or generate this specific type of code snippet.
Got it. Break down the agent's work into potential SLM-sized jobs.
Exactly. Then comes step 4, SLM selection. For each specific task you've identified, you need to choose a suitable SLM candidate.
Based on what criteria?
You'd look at its known capabilities, how it performs on benchmarks relevant to that specific task, its licensing terms that's important, and your own deployment requirements, like can it run on the hardware you have available.
Right, pick the right tool for the job.
Pick the right small tool for the job. Then, step 5, specialized SLM fine-tuning. This is where you use that curated, task-specific data you collected earlier to train your chosen SLM.
To make it an expert at just that one task.
Precisely. And you don't necessarily need massive computation here. Techniques like LoRaLay or QLoRa, these are parameter-efficient fine-tuning methods, can significantly reduce the cost and time needed.
Yeah.
You could even use something called knowledge distillation. This is where you train the small SLM to essentially mimic the outputs of a much more powerful LLM, but only for that very specific task. The LLM acts like a teacher for the SLM student.
So you're transferring the necessary know-how from the big model to the small one, making the SLM highly effective for that narrow job.
That's the idea. Make it a highly efficient specialist.
Okay, makes sense. And the final step?
The final step, step 6, is iteration and refinement. This isn't a one-shot deal. Agent needs evolve, data patterns might change, so it's really an ongoing process.
Keep collecting data, keep retraining.
Exactly. Continuously collect new interaction data, periodically retrain or further fine-tune your specialized SLMs to maintain their performance, adapt to new requirements, and just keep making the overall system smarter and more efficient over time.
So a continuous improvement cycle built around these specialized SLMs.
That's the practical path forward outlined in the research.
Well, we've certainly explored a really compelling argument today for why small language models might be more than just a niche alternative, potentially, as the paper suggests, the inevitable future for much of agentic AI.
Yeah, from their, frankly, surprising power on key tasks to the really dramatic cost savings and that inherent flexibility and suitability for specialized, repetitive jobs, SLMs seem to offer a clear pathway towards AI systems that are more efficient, more adaptable, and maybe more sustainable in the long run.
It really makes you think, as this whole agentic AI industry continues its pretty transformative impact, on white-collar work and probably much more, what does the future look like, where the underlying AI agents are significantly more economical, more adaptable, maybe more democratized?
It raises big questions, doesn't it? How does that change how we interact with technology day to day? How does it influence efforts towards responsible AI development if more players are involved? Could it even help us tackle really complex global challenges more effectively if the tools are cheaper and more specialized?
Lots to ponder there. And it's worth noting the paper itself actually calls for contributions and critique from the wider community. They recognize that advancing this whole discussion, testing these ideas, is really key to driving down the costs and improving the capabilities of AI for everyone.
Yeah, it's an open invitation for more research and development in this direction.
So we definitely encourage you, our listeners, to reflect on these insights. Think about the implications for your own work, your own interests, and maybe even join the conversation happening in the field.